I was always a good student. Okay, a very good morning to all of you. I'll just share my entire screen and then I'll get a confirmation from you whether you can see it. Okay. So guys, I have shared my entire screen. Please give me a confirmation whether you can now see the entire screen as well as I'm audible to you. Hello. Yes. Perfect. What about others? Omni, there we have 9 learners. I hope every one of you is active. You have to be active, honestly speaking. That's the only way I come to know that yes, you are in sync with me. Okay, fine. By the way, have I ever taken any of your sessions earlier? I don't remember, but in case if you can help me out, I mean, do you know me by any chance? Yes, no. Have I taken any sessions for you before? Of course, might have seen my name as well as pic. So, in case if you are able to recognize from this, have I ever conducted any sessions for your cohort anytime before? Oh, wow. Yes, we have attended your other sessions. So that means you know me. Right. Okay. Even I was having this question. You know why? Because of Nigna Reddy. Because that's a very atypical name, right? Nigna Reddy. So I thought that I have seen this name somewhere before. I was a bit skeptical that maybe I have taken your session, but not very sure about that. So yes, perfect. So very nice. We attended your other sessions. Was it only PCA or anything other than that also? PCA, I took it for your batch. Other than that, okay, only PCA was the one. Okay. Thank you, Reddy. Okay. So you all are familiar with my teaching methodology, right? So by the way, I want to know that your Ridge and Lasso's one session is being already covered. So I will like to know how much of Ridge and Lasso is clear to you. I mean, if I ask in percentage terms once again, 0 to 100, how much of Ridge and Lasso is clear to you? Because one session is already being over. So if I just say, please rate it in percentage terms with respect to module and with respect to one live session which was already conducted previously, how much of Ridge and Lasso is clear to you? Okay, Nigna Reddy is saying 50%, about 80% is clear. Okay. What about others? You can just write a number. 30. Okay. So for all others, should I assume it's 100% clear? And you all have come for revision? Because I see replies from only 4 of you. Pooja is saying 30. Prajakti 40. Gargi is saying 50. Okay. Fine. Fine. No problem. Okay. At least I can assume that you know linear regression in and out, right? You know linear regression, right? Because that is a prerequisite. In fact, let me tell you what are the prerequisites. You should know what is linear regression. You should know what is bias. You should know what is variance. I mean, these are the basic prerequisites which are required for today. If you know this, then understanding regularization is going to be very easy for us. So all these things are clear to you. Am I right? Yes. Perfect. Very nice. So, well, then let's get started with the session. My name is Dr. Darshan Ingle. All of you know me, so there is no point in introducing myself once again. Let's get started with the session. And the topic for today is regularization. Precisely, Ridge, Lasso, and to some extent, I will also cover elastic net regression. Okay. Now, if you actually observe the PPT after this, I mean, look at this. Empty. You don't have, all of this PPT is empty. Right, I'll just, there are 33 slides in this PPT. Do you see any material? No, absolutely no material. Start slide followed by the end slide. That's it. Okay, that's because every material is going to be written down over here. There is nothing as such, which can be predefined when it comes to Reg and Lasso. So, so let's get started with this. So I say, just a second. Here is where we have. Let's get started. So the point number one is regularization. That's the main topic for the day, right? So what is basically regularization? Let's try to figure out. Well, if I say, let's say I have an equation like y is equal to 15 plus 1.2 x1 plus 20 x2 plus 39 x3. Okay. In this particular case, I mean, we know linear regression, right? So this equation is pretty much similar to writing y is equal to c plus m1 x1 plus m2 x2 plus m3 x3. What do we understand over here? The point that we can understand from this particular point is x3 is a very important feature to determine y. Why is that? Because x3 has the highest value of the coefficient. You can observe over here, x3 has the highest value of coefficient. Precisely, I say x3 has the highest regression coefficient. And similarly, I say that x1 over here is the least important feature because it has the lowest value of the coefficient, right? Since the value of x3 is too high, working on the data sets become computationally very much expensive. See, we know that as a machine learning model, machine learning says that I want small numbers. Machine learning says, in fact, your computer itself always says that I always want small numbers. For example, even if I ask you a question, tell me what is 2 into 3. All of you will immediately type in the chat section, it is 6. If I say what is 6 into 9, okay, 9 sevens are 56. Okay, if I say what is 23 into 47, and here you start thinking. If I say what is 992 into 496, you start thinking, you start to ponder upon, because you see over here that the complexity has become increased, and because of that the working becomes computationally expensive. The same thing happens with the model also. So we understand over here that since the value of x turns out to be, since the, what is wrong, yeah, since the value of x over here, since the value of x3 is very high, we understand that it becomes a computationally expensive task, and therefore we say that the model also becomes very complex. How to avoid this particular thing? I mean, how can I avoid the model from becoming very complex? And here comes regularization as a hero. Regularization says that I will make the model simplified. Give me the opportunity. Okay, so now since the model has become complex, therefore I say to reduce the complexity, we go for regularization. Okay, how? Well, how, that we'll see. But somehow our equation, which was previously y is equal to 15 plus 1.2 x1 plus 20 x2 plus 39 x3, after undergoing this particular part of regularization, gets transformed to something like this. So I get my y is equal to 0.9 plus 0.7 x1 plus 2 x2 plus 5x3. I mean, the regularization, I mean, from this, it is very much clear to us that it is as good as scaling the values down proportionately. The one that you saw, standard scaling, min-max scaling, robust scaling, so it's pretty much similar to that. But anyways, if it is with respect to the equation, we call it as regularization. And now you can see the number which was 39 initially has become 5, and all others are proportionately reduced. And therefore, I say this becomes a computationally easy task. So we understand why do we go for regularization. Now, since this is clear to you, it is important for us to understand what all are the different types of regularization. Well, broadly, I will say, sorry, the first type of regularization is ridge and the second type is lasso. The third one is also there, but I'm preferring not to write it with a solid line, which is called as elastic net. We will be discussing that, but let's not consider it as a type of regularization, although it is. You'll understand the reason why. Okay, so let's get started with the very first one. By the way, till this particular point, is everything clear? And one more request to all of you, don't get confused with the older session, okay? Take my session altogether as a fresh one. Sometimes what happens is learner immediately starts comparing, but in that session, I was told like this, I was told like that. Well, all of these concepts are altogether going to meet at the same point. I try to explain it my way so that, it becomes much more simplified for every one of you to understand. That's the only agenda. So the concept definitely is going to remain the same, but still, don't correlate it with the previous session. Please don't correlate it with the module either. But ultimately, all of them are the same. So are the things clear so far? Whatever we discuss in the PPT, is that clear to you? Can I move on with the ridge regression now? I'm asking this question to everyone, not only Gargi and Nigna Reddy. And okay, because I expect a reply, else I will stop asking questions and I will lamely go on with explaining the concepts. Then what will happen at the end of the day, since I'm not looking into the comments, you will say that I'm ignoring the comments. That should not happen. Therefore, it is very important that you periodically tell me whenever I ask you that, have you understood the concept? That's very important. And that also motivates me, honestly speaking. Obviously, in 13 learners, if I don't get a reply, I mean, it's a very bore way of delivering, right? Perfect. So let's go ahead. Getting started with the first one. Now, let me tell you how am I going to go about it. Initially, I am going to give you an overview of what is ridge regression, overview of what is lasso regression, and overview of what is elastic net regression. I repeat, initially, I am going to give you an overview of ridge, lasso, and elastic net regression. And then after that, I'll be once again revisiting this, wherein I'll be exploring the mathematical, or precisely, I would say the geometrical aspect of this. So initially, I explained you what is regularization. Now let's understand what are the three types of regularization and how are they performed. We will understand it later in the third stage. In this way, we have stage 1, stage 2, stage 3. Stage 1 is where I introduced you what is regularization. In this, I'll be introducing you to the types and the advantages of it. In the third way, we will be going on to the geometrical intuition behind each of this. Okay, so what I'll be doing right now is explaining you what is lasso regression and how the results of lasso regression are going to look like. But how are they computed? Let's discuss it in the third phase. There is a reason for that. I mean, if I explain you the geometry also at the same time, you may end up asking me a lot of questions, which at the end, all of the learners will be confused with. So let's divide it into stages, and my sincere request to all of you is to stay connected with me, and whatever I teach, if you are able to follow that, you are on the right track. don't think a level ahead of that. Don't compare it with the previous session. Don't compare it with the module. As simple as that. So talking of the very first one, which is called as ridge regularization. Well, let me tell you, ridge is also called as a L2 regularization technique. In fact, many people don't even call this as ridge regression. They call it as L2 regularization technique. So you have to understand that L2 is nothing but ridge regression, and similarly lasso is L1, other way around. Okay. Now, what is exactly ridge regression? Ridge regression says that my loss, and the value I'm going to calculate the regression is loss plus some value lambda into the square of this. Okay. Now let's think of this one by one. The first thing, when I talk of loss, now we know that there are various metrics for loss, but let me initially talk of loss over here. And let's say on our graph, well, this is maybe the line of the best fit that we have plotted using the linear regression. Now, the model has predicted the point over here. Okay. The model has predicted the point over here, whereas the actual point, this is the actual point over here. Now what do you see over here? Well, the distance from the actual point to the predicted point, this particular thing, this is called as the loss, or we also call it as the residual error. And we understand over here that greater is going to be the difference, the greater is going to be the loss. Greater the difference, greater is the loss. So therefore we say greater the difference, greater the loss. So now we understand what is this particular term when it comes to regression. So ridge regression says that every time you are going to predict for me, this is the loss that you have, and loss is going to be calculated like this. And there are various metrics for that. This is something which we actually already know. Now coming on to the next part, we also have a term which is called as penalty. Let me write it in black. Now this term which you have over here is called as penalty. Okay. What is exactly penalty? Well, let me write over here. My penalty is going to be nothing but lambda into w square. Okay, I'll discuss each of this thing. So I'm talking of the second term inside this. Now, why is this penalty? I mean, why have we even added this term which is called as penalty over here? The reason for adding penalty is so that I can reduce the loss. Precisely, we try to compensate here for the loss. See, let's say I'll give you a very practical example. Let's say because of me, someone suffered a loss of 1,000 rupees. So I say that, yeah, it's very bad. I'm not liking it because of me, you suffered a loss of 1,000 rupees. I cannot contribute entire 1,000 rupees for your loss, but I give you 500 rupees so that at least your loss is minimized. So I say over here that if someone is in a loss because of me, I am going to give some kind of aid to him, which is in the form of penalty, so that the loss is minimized. So precisely when I talk of penalty, we try to compensate here for the loss, that is reduce the loss. Precisely, I am scaling down the magnitude of the coefficient. So to just write about this, I say penalty is imposed to reduce the loss. Precisely, we try to compensate here for the loss. The main advantage, what is the main advantage of this? Well, it helps us to scale down the magnitude of the coefficient. That's exactly what we studied. Magnitude of the coefficients. Okay, so we understand what is penalty altogether. Now let us individually try to understand what is my lambda. What is exactly my lambda? Well, lambda is any constant value. It can go from 0 to any positive value as high as you want. So you can just consider lambda as some kind of jugaad that we are adding over here so that we can penalize the loss. I'll explain the significance of lambda in the third stage, not right now. Okay, right now let's try to understand what is ridge regression and what is this term. Well, this term is nothing but W1 square plus W2 square plus W3 square plus dot 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 plus Wn square, where I say that W is a vector of coefficients, and you know what are coefficients. In our equation, what are the coefficients? 1.2, 20 and 39. These are nothing but the coefficients. So now we understand over here that this is what is the advantage of it. Now how this thing help, we will see it in the third stage, but let us try to understand the equation over here in this stage. So lambda is any constant value which can go from 0 to any positive value. My mod of W square is nothing but W1 square plus W2 square right up to Wn square. Well, W is nothing but the vector of coefficients. Now let us try to analyze the results and then we'll see how do we get those results. So initially, if I want to analyze the results, so I go to the next slide and say over here, now let's understand how does the addition of penalty, how does the addition of penalty reduces for the loss. Okay, now I'm just directly projecting you the results over here. So let's say if I have a plot something like this, now I have to decide on the value of lambda, that is what is in my hand. If I decide the value of lambda as 0.01, on the x-axis what I have is the coefficient value. This is going to be positive and this is going to be negative. Okay, don't compare it exactly to the equation which I just showed you sometime before. Let's compare it in the generic way. Okay, if I compare it in the generic way, what is going to happen over here is if you have alpha is equal to 0, 1, this was the initial magnitude of this. And let's say if you have a negative also, this is how it is. This is the standard way of representing it. Okay, it is not related to any specific equation. So if you observe the alpha value when it is equal to 0.01, this is where it is going to intersect the positive axis. Similarly, something like this, similarly something like this, similarly something like this. Okay, so this is what we have over here. Let me try modulating the value of alpha to 1 and try to understand the changes in the same diagram. Everything remains the same, but the value of alpha when changed to 1, this is positive, this is negative, and this is my coefficient value. In this case, what is going to happen is this value which was so big will now be transformed to this. Obviously this will be proportionately reduced. Okay, The second value, how many we have? 1, 2, 3, 4. This is second, this is third, this is fourth, this is second, this is third, and this is fourth. So you can see that increasing the value, or not alpha, I'm sorry, it is lambda. Okay, it's lambda. It's always going to be lambda only, not alpha. If I change the value of lambda to comparatively higher value, we see that the magnitude of the coefficients have reduced. How? Let's see that later in stage 3. But increasing the value of lambda reduces the magnitude of coefficients. Let's say I further increase it. So this is the plot. Once again, I am plotting. These are my coefficient values. This is my positive value. This is my negative value. Let's say I increase the lambda value to 2. In this particular case, this gets converted to more smaller value, 2, 3, 4, 2, 3, 4. So you can now see if I map it over here, and if I map it over here, we understand it very clearly. So what is plotted over here is on this axis, basically what we have is my variables. So here comes a very important point to conclude. So I say that it is my lambda value which basically modulates the magnitude of coefficients. So therefore I say over here that greater the value of lambda, lesser is going to be the value of coefficients. Greater the value of lambda, lesser is going to be the value of coefficients. I mean, how, that we don't know, but looking at this diagram, certainly you can trust me and understand that higher the value of lambda, smaller is going to be the coefficient. So just like to note a few points over here, and for that I'll just change the ink color. So to make a note of the few points, I see over here that compared to the older techniques, certainly it is more computationally efficient. Second advantage over here is it penalizes large numbers more. That's exactly what we see over here. It penalizes large numbers more. How? We will see that. Hold on for that. Third is, this particular technique is comparatively much more popular. And the fourth and the last one is, it is also considered as a good technique even when you encounter collinearity in the data set. Even if you have collinearity in the data set, this technique turns out to be one of the fantastic techniques. Okay, so this is how my ridge regression helps. At least this application of ridge regression and what it does overall is clear to all of you. Yes, are the things clear so far? How does ridge regression help? Can I assume this as transformation? Nigna Reddy, yes, you can assume it as transformation, but don't take the term very seriously. But yes, it is transforming something to smaller magnitude. Yes, perfect. Thank you very much. This is the kind of reply which I expect. Very good. Now, I'm not getting into the how of it. That is the third stage. Let us now discuss lasso regression and then elastic net regression, and then we'll get into the how of it. So here comes the second one, which I talk of my lasso regression over here. Well, let me tell you that lasso is going to use L1 regularization. Remember these names, okay? People usually, in interviews, they ask you, do you know anything about the L2 regularization technique? So you should understand by default it is ridge only. Without getting confused over here, by default it is ridge only. So we understand over here now. How is lasso calculated? Okay, Now, why is the formula like this? I will talk of this later, okay? Not right now, but I will certainly answer that question. So if I take into consideration the lasso, the formula is loss plus lambda into W. Once again, if I talk of that particular thing which you have at the end, this particular thing, loss is something which remains the same. This is called as the penalty, and this time I need not introduce you what is penalty. You know it very well, but the only difference over here is lambda is lambda only. That is again the same thing, and W is nothing but the vector of coefficient. But if you remember, the square symbol has gone. If I just compare it back with the older slide, you can observe over here at the top or over here in this equation as well, it is lambda into W square, whereas in this case it is lambda into W. What is my W over here? W is W1 plus absolute of W2 plus absolute of W3 plus absolute of Wn. Okay, so what exactly happens over here? Well, over here also the regularization is going to happen. The coefficients are going to be reduced, but I'll just give you a hint, what happens over here. I just showed you in the older one. I mean, here, let's say, I'm sorry. Yes. This is, this thing, y is equal to 1.5x plus this, where this older thing happened. This actually happens in my ridge regression. So if I want to say it, I'll just write it over here. When it comes to ridge regression, I'm sorry. Ridge regression, what actually happens is this. So if I have something like, where is my pointer? Yes. If I say, for example, my y is equal to 15 plus 1.2 x1 plus 20 x2 plus 39 x3. Okay, listen to me very carefully. What happens when I undergo ridge regression or ridge regularization is my y is going to have reduced coefficient, and my y becomes as small as 0.9 plus 0.7 x1 plus 2x2 plus 5x3. Wait a minute. Learn this equation because I will not be able to come back. If you observe over here, 15 got transformed to 0.9, higher than 0. 1.2 got transformed to 0.7, higher than 0. 20 got transformed to 2, obviously, which is greater than 0. And 39 also got transformed from here to 5, which is higher than 0. Why am I stressing on higher than 0? You'll understand it right now. So if I go to my lasso now, if I look at lasso, well, in lasso, if I narrate the same example for you, where I say y is equal to 15 plus 1.2 x1 plus 20 x2 plus 39 x3. When I ask this equation to go through my lasso regularization, what happens is something like this. My y get transformed to 15 becomes 0.9. This becomes 0x1 plus this becomes 0x2 plus this becomes 5x3. What do you understand over here? It clearly understands that among these three coefficients that you have, that is, you have this, and this. Okay, these are nothing but three independent variables. Among these three independent variables, lasso actually got rid of this, and what is kept over here in the equation is nothing but y is equal to mx plus c. So not necessary that it will be getting rid of all the coefficients except one. It can also transform. Let's say we have an equation like m1x1 plus m2x2 plus m3x3 plus c. This can be transformed to y is equal to m1x1 plus m3x3 plus c. Precisely, my m2 becomes 0. I mean, That's all. Sorry, my x2 becomes 0. This is possible. It can very much be possible that both of this become 0. Who is going to decide that? Once again, it is going to be the lambda which is going to decide that. Okay. So before I conclude anything, and you have observed that how is my lasso doing? My lasso is basically trying to make some of the values as 0. What is the advantage of that? We will see it later. But first of all, let's try to look at the intuition behind it by plotting it onto the plot, just like we did over here for this particular graph. So I say, I have, after this, the same thing over here. I have my coefficients. This is positive. This is negative. Initially, it is as high as this. So you can actually have a dotted line representing this. The next is 2, 3, 4. 2, 3, 4. Now this is when the value of lambda is 0.001, and just an assumption, okay? It can be 0.01 also. I'm just taking it for comparison. Then when I actually after this tend to increase the value of lambda to 1, these are my coefficients. This is my positive, this is my negative, and what do you see is, first and foremost, this got reduced heavily. We are happy with this. This got reduced heavily. We are happy with this. And thereafter, that's it. You don't see the middle two features. You can see over here, the middle two features have vanished. Well, that's exactly what I showed you in the previous slide, right? Some of the features, some of the coefficients can become 0. And that is the reason you see over here something like this. Well, if I say my lambda is further increased to a value as high as 5, in this case, you can see one coefficient over here, one coefficient over here, okay, just like this particular thing. In this one coefficient over here, one coefficient over here, and all of this is empty. This is my coefficient, this is my positive, this is my negative. Now, here I come to a conclusion. If ever you think that there is a confusion between ridge and lasso, what did you observe in ridge? In ridge, if you observe the equation which is stated in this example, in ridge you observe that the coefficients never become 0. It never becomes 0. And let me tell you, the simplest answer for the reason for it not becoming 0 over here is because we are taking the square of it. In this case, we are not taking the square of it, and that is the reason that it can become 0. How? I will tell you. Just hold on with that. But with the help of lasso, one thing is sure, that some of the coefficients are getting eliminated. What do you understand by that? Let's say I am trying to predict the price of the house. My price of the house is dependent on the sector, is dependent on the size, it dependent on whether the hospital amenities are there nearby, it dependent on the schools. And if this is the kind of problem statement that we have, where these are my independent features and this is my dependent feature, what is my ridge going to do for me? If you have a value over here, maybe like 39, 26, and 3, it will ensure that all of these 4 values are scaled down. Okay, but they will not become 0. But lasso, depending on the value of the lambda, can also transform few of the values to 0. This is what is observed in lasso. So when I say this is 0, that means size and sector are not selected at all. That means size and sector are not selected at all. That means size and sector are not selected at all. Therefore, I say lasso also acts as a feature selection technique. Therefore, I say lasso also act as a feature selection technique. In fact, that is how lasso is different from ridge. Are you able to get this thing? Lasso is different from ridge in the only way that it is acting as a feature selection technique. So the most important features, which is the one which is having higher coefficients, as Anaga is saying, will only be retained. All of the other values would be made as 0. So yes, as Gargi is saying, larger the value of lambda, higher is going to be the elimination of the features. Are you all able to get it? Yes. Now the next thing after this we want to see is how does it actually work. But anyways, are the things clear so far? Lata, what is the issue? Lata is saying no. What is the issue, Lata? Just everyone is saying yes. I'm not able to understand the lambda. See, lambda is just a regularization parameter. See, it is like now, let's say you are using a radio at your home, okay, or your car's music system. What is lambda? Well, lambda over here is the volume controller of your music system. You increase it, you get larger volume. You decrease it, you get smaller volume. You increase the volume, you get larger amount of voice. You decrease the volume, you get smaller amount of voice. In the same way over here also, it is basically lambda with the help of which this all thing is happening. Higher the value of lambda, higher is going to be the number of features that are going to be eliminated. So if you have really very large number of independent features, then only you go for lasso, else you will go for ridge only. If you are interested in feature selection, then only you are going to go for lasso, else you will be going for ridge. And what value of lambda you are going to select is purely going to be a hyper parameter choice. When I come into the notebook, when I show you the execution of that, you'll understand why is it a hyper parameter choice. Are you getting it, Lata? Yes? Okay. Gargi is saying, can you repeat the answer for the question I asked? What did you ask? First of all, let me see. I don't remember. So the lambda is more, the variable is 0. Yes, Gargi. The more value of lambda, the more is going to be the number of the features that you are going to eliminate over here. Larger lambda, as you can see, lambda 0.01, this is what we have. Lambda is equal to 1, it's get reduced and some of them gets small as 0. And over here, further increase the value of lambda, more number of features to be dropped out. That's exactly what you see in this example also. Okay. Now, this example, depending on what value of lambda you choose, depending on that, this equation would be there. So it can be 1 zeros or it can be all zeros. So you have to ensure that you should not give a very large value of lambda also. So what is the ideal value of lambda? There is no answer to it because it purely depends on how many features do you have. If you have 250 independent variables, then your lambda can go as high as 5, 10, 15, 20, 30. If you have just 20 variables, then your lambda can stop at 1 or 2, because after going to 3 you will see that all of the features become 0. So it's a hyperparameter choice. You have to try it, and for that we are going to use the grid search CV algorithm for trying out the different combinations. Yes, clear to you, Gargi? So Srijesh is asking, when the expression does the straight multiplication between lambda and coefficients, how the coefficient reduces. Srijesh, I just told you this is what we are going to see in stage 3. I'm repeating this at least for 5th time from now. When we come on to the stage 3, I will tell you how this thing happens. Okay. Whatever doubts you have, please write it in the chat section only rather than going to the doubt section. Okay. That will be easy for me also to monitor at one place. Okay, Srijesh. Then Ajinkya is saying for feature selection, lasso. Then when to use ridge? Can you repeat? Ridge has to be used when you don't want to go for feature selection. If you just want to reduce the magnitude of coefficients, then you go for ridge regression. If you want to do feature selection by making some of the magnitudes at 0, then you go for lasso. Simple. Clear to you, Ajinkya? And Gargi, I answered your question also here. Okay, when to use what? Perfect. Very good. So now let us document the things. So I say over here, when I talk of lasso, it also acts as feature selection. In fact, I say that's how it is different from ridge regression. That is the first point, by the way. The second point over here, I say that also, comma, lasso is more robust to outliers. Yes, it is a tried and tested thing. Lasso is much more robust to outliers. Now let us discuss the last technique very fast and then go to the stage 3. And the last technique over here is elastic net regression. So the third one is elastic net regression. Okay. Now, first of all, let me tell you why is it called as elastic. It is called as elastic because it is taking the advantages of both ridge and lasso. So I say it is taking the advantages of both ridge and lasso. Okay. So just to revise in short, how did my ridge actually work? My ridge used to say that it is going to be loss plus lambda into coefficient square. Then was my lasso, which used to say that loss plus lambda into absolute value of coefficient. So what is my elastic net regression? Well, if I talk of my elastic net regression, it says that it is going to be loss plus lambda 1 into coefficient square plus lambda 2 into magnitude of the coefficient. That is how it is different. So if you observe the formula for this, it has got the combined advantage from ridge as well as lasso. So now let us try to understand when to use what. Okay, so I say when to use what, when to use what. First of all, if I talk of ridge regression is basically used whenever we have a multi-collinearity problem in the dataset. I hope everyone knows what is multi-collinearity problem. Yes, do you all know what is multi-collinearity problem? Very good. So, ridge is used in the datasets which have multi-collinearity issue. Precisely, it is when the independent variables are highly correlated with each other. Second is, when do we go for the lasso? Well, lasso is used, I think I already told you, it is used for feature selection. Okay. And third one, so it's not like that any data set is there, you stop using linear regression and you directly go to ridge regression. No. understand when it can be used. When you have a lot of multicollinearity, then it makes sense to go for ridge regression. If you want to do feature selection, then you can go for lasso. And coming on to the third one, which is called as the elastic net regression. Well, I say over here that it inherits the advantages of both. In fact, it is elastic in nature. That's what I say over here. Precisely, I say that it is flexible in nature, and therefore elastic net regression is a hybrid of ridge regression and lasso regression. So when you want to have the combined advantages, you can use that. But I am not still concluding that elastic is the best. Okay, just because you see that it has advantages of both, don't go for elastic. Let's say in your data set, the number of the features are already very small. You don't want feature selection to be done. In that case, why will you go for elastic net regression? You go for that if and only if you want to do feature selection. Else, it doesn't make any sense to go for elastic net regression. You can go for lasso when you want to do feature selection. When you have multicollinearity issue, you can go for ridge regression. So make a note of all this thing. Is this thing clear to you? Lata, real life example, why do we need to have multicollinearity example? Well, multicollinearity example is, let's say, okay, let's say this is, I am trying to have an independent feature which is called as height. From the height, I want to predict the weight. So let's say this is the height of the person, this is the weight, this is the height, this is the weight, this is the height, this is the weight. Okay, let me tell you that this is the height in centimeters and this is the weight in kilograms. So from the height, I am trying to predict the weight. Let's say I have one more column which is called as height, but this time the height is in meters. I say that this column and this column are having collinearity among themselves, because this is also responsible for predicting this. This is also responsible for predicting this. Honestly speaking, both of them are equally responsible and both of them are doing the same thing. So in that case, it makes sense to drop off one of these columns. In this case, when you have two columns to be having the same effect for predicting y, this is called as a collinearity problem. If you have one more column called as x3, which is also equally responsible for predicting y, then I say that it is a multicollinearity problem. Okay, and over here, if you don't address it, unnecessary computations will be taking place and your y will be heavily dependent on x1, x2, x3, whereas x1, x2, x3 are doing the same thing. So it doesn't make sense. See, it is like if you want to go from one place to another, and if you have 3 cars at your home, you are not going to take all of the 3 cars with you. You are going to sit in one of the car and go. Just because you have 3 cars doesn't mean that you are going to carry all the 3 cars along with the chauffeurs from one place to another and sit in just one car. It doesn't make sense. And the same thing is happening over here. For predicting the weight, one of the feature is important. X1, X2, X3 altogether are not required at all. So use only one of it. Are you getting it now? Yes. This is called as the multicollinearity problem. Collinearity can be simply said that if x1 is correlated to x2, then we say it is called as a collinearity. If x1 is correlated to x2 is correlated to x3, more than 2, if you have more than 2 independent variables which are correlated, if you have more than 2 independent variables which are correlated, that is called as multicollinearity issue, in simple words. Clear to you, Nigna Reddy? Okay. Lata is saying, okay, welcome. By saying, might be asking a very layman question, not a problem at all. Why do we have a model using ridge as we never expect to have multi-collinearity? As you said, we drop it. See, if you are dropping it, that's well and good. But if you are not dropping it, okay, see, for you to drop the multi-collineative features, I mean, Lata, in this case, you will find it very easy to drop the multi-collineative features. You know why? Because there are hardly 5 to 7 columns in the screen, as you can see. Okay, so maximum how many can I add? 5, 7, 10 columns. But if you have 60 columns, are you going to introspect each of the 60 columns manually? Won't you think that is going to be a very much tedious task? So how many pair plots are you going to make, and how much analysis are you going to do? That is going to be very much cumbersome procedure, and therefore at that time we can't think of using the drop function to be used every now and then, and you go for automated approach. That's exactly what we are talking of. So you can go for Reg in that case. Clear to you, Lata? Okay, very good. Now let's go ahead. Samir, while also when we can use random forest thing. So, your question is as simple as saying that why do we have buses in Mumbai city when we have local trains? Why you have local trains in Mumbai city when you have cars? Why you have cars in the city when you have motorcycles? Why you have motorcycles in the city if you have bicycles? Does that make sense to you? Are you getting it? They are options, different ways to do the same thing. Okay. Pratima is saying, in real life, mostly we will be having many features. So there will always be a problem of multicollinearity and feature selection. So we have to choose elastic net. No, Pratima, that's not true. When you actually start working with the real-time data set, you'll realize that sometimes sometimes the client itself doesn't allow you to drop some of the columns. Some columns are very important, but the model says that this columns can be dropped off. But if the client says no, this is something which is very important for me, you cannot drop it, in that case you cannot go for that. So all of these are options given to you, and just don't come to a conclusion that elastic net is the best. No, that's not the case. It purely depends on the problem statement. What is the requirement of the client? Is it feasible to drop it? If there is no such constraint from the client, then yes, you can go for elastic net regression. But you have to also understand that by dropping some of the features, you are also losing the data. Is it really worth? If by using ridge regression, you are getting the mean square error of 965, and if by using lasso, you are getting it as 960, and if by using elastic net, if you are getting it somewhere in between, that clearly indicates that elastic net is not helping in that particular case. Don't go for it. So be very careful. Don't go with a static approach saying that this is what is going to help me in all of the cases. Perfect. So having understood the thing so far, now we can go on to the third stage of it, where we discuss the mathematics. Yes, welcome, Pratima. So third thing, let us try to understand the ridge and the lasso regression with the help of the geometric intuition behind it. So I say, initially, I'm only going to discuss over here the ridge and lasso, not the elastic net regression. That is by default covered. Okay, we are not going to talk of elastic net after this. Implementation wise, also it is going to be very much similar to what is done in ridge and lasso. So now let us say I have a data set over here. In my data set, let's say this is the independent variable, which is the experience of an employee, and this is the dependent variable, which is the salary which we want to predict. Okay, now if I say over here that I have certain points, okay? Based on the experience, I have these all points. Now, what is the task in linear regression? The task in linear regression is to draw a line which can pass through this, which is called as the line of best fit. Now, what is the advantage of the line of best fit? The line of best fit is the one in which we have the least residual error. That is, if I try to calculate I is equal to 1 to n of my y actual minus my y predicted the whole square, I get this value to be minimum. We know this, right? Y actual minus y predicted the whole square. Now again, why do we do the whole square over here? That is just a choice, okay? Initially, if you observe the mean absolute error, it used to take y actual minus y predicted absolute value. Then came the squaring of it. Okay, so this is why squaring happens to be better. I mean, I hope you know why we go for squaring of the things and why not just y actual minus y predicted. Do you know this or you don't know it? Do you know why we go for squaring of it? Or should I explain this to you very quickly? Yes, to accumulate the total error to get the sense of magnitude. But why specifically squaring? Well, uh, so that the residuals don't cancel out each other. Correct. To remove the negative values. That's perfect. See, you got to understand. I'll just take a simple example for you. Let us say if I have some values, maybe plus 4, -4 and -4. So initially the technique which was used for calculating the error was to calculate the average of it. So this is how far, this is the actual value, this is the predicted value, the distance is +4, this is the actual and this is predicted, this is the actual and this is the this is predicted, this is actual, this is predicted, this is actual. So now I can say, I can simply add up these values. 4 plus 4, I'm just using the mean formula, plus -4 plus -4 whole thing divided by total 4 points are there, so that is going to be 0 out of 4, which is 0. So do you mean to say there is a 0 error in this? How is that possible? The points are not on the line, so 0 error is just not possible. So we come to a conclusion that yes, this is a wrong metric. So if you go for the mean of the values, that is a wrong metric. So let me go for absolute of it. So I say mod of 4 plus mod of 4 plus mod of -4 plus mod of -4 whole thing divided by 4. That is going to be 16 divided by 4, which is 4. Now this is something which seems to be good to me. Okay, now that actually takes me to one more problem. If I have +7 and let's say +1 over here, and if I have -6 and I have -2 over here, if I go for the same thing using the absolute formula, that is going to be mod of 7 plus mod of 1 plus mod of -2 plus mod of -6 whole thing divided by 4, which I have 7 plus 1 is 8, 9, 10, 10, and this is 16 divided by 4 is equal to 4. Yes, that's right. So do you mean to say that the error in this case, if I call it as case A, and the error in this case is the same? No, it's just not the same. You can see over here, the errors are as small as -4 and as large as -4. Over here, the errors are as small as -6 and as large as +7. Observe the range. This goes from -4 to +4. That is -4, -3, -2, -1, 0, 1, 2, 3, 4. So total the spread of the data is across the 8 points on the number line. Over here, it goes from -6 to +7. So 6 and 7. The spread of the data is 13 points on the number line. How is that possible? It's practically not possible. And therefore, I again conclude that this is again a wrong metric. And this is also a wrong metric. Okay, see, that is the reason these metrics are not popular nowadays. And here comes that, and I think of taking the square of those values. So now let us consider my case A. If I consider case A, that is going to be 4 square plus 4 square plus minus 4 square. I want you all to compute the answers. I'm not going to move to the calculator. Plus minus 4 square, the whole thing divided by 4. Please tell me the answer for case A. Till then, I will write the answer computed for case B. That is going to be 7 square plus 1 square plus minus 2 square plus minus 6 square, the whole thing divided by 4. Okay, please tell me the answer for case A. That's 16. Okay, it's 16. Okay, I'll write it as 16. And what is 16 or 256? Answer for case A. I mean, please write A dash so that I understand which answer are you writing. It's for A or it is for B. A is 16. Okay, A is 16 and B is 22.5. Okay, and what is the square root of this? If I take the square root of this entire thing, please tell me the answer. This is 4 and this answer turns out to be square root of 22.5. 4 point something would be there. Square root of 22.5, exactly 4.5. So many answers. Just tell me to 3 precise digits if you can get. 4.743. Okay, let me take that. Okay, so now it's pretty much convincing that yes, over here the spread of the data is just 8 points, therefore the error is 4. Over the spread of the data is 13 points and therefore the error is 4.743. That is the reason you go for squaring. Is this logic clear to you, everyone? Okay, so now, I mean, now you may say that why not cube the data? Why to increase the complexity by cubing it? See, we were in the process of finding the best answer. That's what we found out. Why to increase the complexity by cubing it? Now you can also take the cube, you can also take raised to 4, raised to 5, raised to 6, but not required. Try to keep it simple. Okay, so this is the formula which was invented over time. And squaring as such has no significance. It is just an outcome of trial and error process. So there is nothing, absolute no reason as to why are we squaring it. But just because power of 1 was not helping me, I went to power of 2. In case a power of 2 was again causing a problem for me, then I may go to power of 3. So it is again a hyperparameter which actually we changed over the years gradually. Similarly, in our case also, we have lambda. That is something which is nothing but which we are going to change gradually in such a way that we come to the solution. So now, here is what we see. Okay, so now I think before proceeding, it's what is the time? 13. I need to launch the polls. Just a second. I'll just launch the mid-session polls. Request you to please fill it up. We have 20 participants. Request you to please fill it up, guys. I'll be just back in a minute. Okay, 16 received, 4 not received. Request you to please fill it up. I'll be closing it in next 10 seconds. I'll be withdrawing the feedback. Mm, 17 received. Okay, I'll withdraw it now. Oh, it's done. Uh, where can I get this form? I'm using mobile. Sandeep, I don't know. I only know that I have to launch it this way. Other than this, I really don't know the background working of it. I think the best option is please talk to the student mentor. He or she can help you with this. Okay, they can share you the link. Okay, mobile also gets a form. I really don't know because I don't know how is the student interface at your side. Okay, so let's go ahead. So now we understood that this is how the thing is. Now, but there is one thing that we need to do understand over here, that every time we do this and then we predict for some value of x. Okay, we predict for some value of x, the corresponding value of y using the line of best fit. Okay, but to check whether this line of best fit is really as expected, what we do is we divide the data into train and test set. Now let us assume, okay, I'm just assuming that this is my data set, which is the same. I have expenses on the x-axis, I have salary on the y-axis, and I have just two data points. This is my first data point and this is my second data point. Now, if I am calculating, or rather say if I want to draw the line of best fit over here, we all know that the line of best fit can be drawn over here as simple as like this. Okay, this is going to be called as the line of best fit over here. This is my first point and this is my second point on the line. So if I think of the sum of residuals over here, which is nothing but summation of I is equal to 1 to n y actual minus y predicted the whole square, this is going to be equal to 0, and I'm really happy with this kind of thing. So the sum of residual is 0. And what was my aim? Well, my aim was the same. My aim was to minimize the loss. You remember in the earlier slides also we said that our main aim is to minimize the loss, and we are very happy to see over here that the loss is 0. I repeat, we are very happy to see over here that the loss is 0. But now, as I told you, that my data actually consists of training data and test data. So let's say this is what is the training data which I have, and it has only 2 points. Now comes the test data. Let's say the test data is maybe a point over here. How far is this point from this line? By this much point. Let's say there is one more test data which is over here. How far is this point from this line? Here. One more data which is over here. How far is this over here? One more test data which is over here. So now what I see over here is whenever I am talking of the training data, I see over here that my error is equal to 0. But whenever I talk of my testing data, I see that I have a significant amount of error. You know what? This clearly indicates that the model is overfitting. What do you mean by overfitting? If you have 0 error on training data and higher error on the testing data, you understand that the model is overfitting. And if you have higher error on training data and higher error on testing data both, we say that the model is underfitting. So this is the case of overfitting. This is what we encounter over here. Now, why does this happen? Well, this happens over here. The reason for this happening is pretty simple, that whenever you are talking of the training data, the error is zero. So I say over here that there is absolutely no bias. Okay, but when I talk of testing data, I see that there is a high amount of variance. That's exactly what I told you should know at the start. Whereas, what do we expect? We expect a model which has low bias and low variance. And by the way, what you just received was no bias and high variance. I mean, no bias and low bias. I'm happy with it. But high variance is something which is not good. So now I will try to balance this. Okay, so it is like something like I have this thing and I want to balance this. Currently, I see that the bias is very low, but the variance is very high. So variance is over here and bias is over here. How can I ensure that I increase the bias so that I can decrease the variance so that they can balance out? Currently, this is where my bias is. This is where my variance is. Bias is as good as not there, but variance is too huge, and bias is as good as not there. What I will say is I have to find a sweet spot, which is called as the bias variance trade-off. I have to find that sweet spot so that it's okay if I increase the bias to some extent, because still no bias would be converted maximum to low bias. But variance which is very high, my variance can become comparatively low in that case. How to do that? Well, let's think of that. Are you able to understand this concept which I have explained on the slide till this particular point? I have to increase the bias so that I can reduce my variance. Zero in training and zero in testing is not an example of overfitting. It is called as the best fit. 100% accurate model, Gargi. 100% accurate. Okay. Now, okay, Gargi. Let's go ahead. So we understand that to address such a kind of scenario, I mean, although we are happy with the line of best fit, this is not actually helping us. And this makes me to modify my cost function or the loss function. So what I see over here, what I say over here is, what am I going to do is, I say that my loss function, I am going to modify it. And I'm talking of which particular thing? I am talking of ridge regression over here. What happens in this case is I say my loss function, which is I is equal to 1 to n, which is y minus y actual, the whole square. I am going to add with this lambda and W term, which you remember, which I now rename it as slope, and I take the square of it. Now, why taking square of it? Just the answer of this is exactly same as I explained you the reason for why we are taking square of the error. Initially, we took the mean, we were not happy, then we go for absolute. Again, that was disappointing it in finding the spread of the data, and then we thought of squaring it. Similarly, over here also, initially squaring it happens to be a good idea. Okay, so now what is the advantage of it? And for that, I will like to redirect you to a new concept which is called a slope of the line. Since you are done with linear regression, still I'm taking you to the slope of the line, and there is a reason for that. So yes, first and foremost, how do you calculate the slope of the line? The slope of the line is calculated as change in the y upon change in x. Now you will literally shout at me as to we all know all these things, but there is a reason for that. So please hold on with me. So if I want to calculate the slope of the line, This is the line. I assume any 2 points on the line, find the coordinates of that. Of course, if this line is drawn on the graph paper, finding the coordinates is not at all going to be a difficult task. I do that. Let's say this is my point A, which is x1 y1, and this is my point B, which is x2 y2. So my slope of the line is y2 minus y1 upon, I'll write it over here. Slope of the line is going to be y2 minus y1 upon x2 minus x1. So which I further say is going to be, what is the value of y2? 6 and y1 3. 6 minus 3 upon 8 minus 2. 8 minus 2, which is going to be 3 upon 6, which is 1 by 2. The slope of the line is 0.5. Now some people, those who are new to this, they are like, why do you assume this point as A and this point as B? So I say, okay, if you are unhappy with that, I will do it other way around. Let me assume this point as A and this point as B. So this becomes by x1 y1 and this becomes my x2 y2. So this was as per case A. As per case B, what is my y2 minus y1? 3 minus 6. 3 minus 6 upon x2 minus x1 is 2 minus 8, which is minus 3 upon minus 6, which is still 1 by 2, which is 0.5. Okay, so I understand over here that this is the slope of the line. Okay, this is one concept that we understood. Apart from this, let me tell you that if you want to calculate the slope of the line, if you have a line which is running like this, you have to observe the first point and the last point of the line. Okay, and you see whether if this line is moving in a positive direction, if this line is moving in the upward direction, you say that it is going to have a positive slope. If this line is moving in a negative direction, in the lower direction, it is called as a negative slope. And if there is a line which is exactly parallel to the axis, we say that the slope of the line is equal to 0. This is again something we know, but I'm once again revising it as a concept. So slope can be positive, slope can be negative, slope can be 0 as well. One more thing which I want you to understand is that if you consider this as my line number 1, consider this as my line number 2, consider this as my line number 3, and consider this as my line number 4, let me tell you that the slope is highest for line 1, followed by line 2, followed by line 3, followed by line 4. And you know why is that particular thing? Why is the slope for line 1 highest as compared to line 2, as compared to line 3, and compared to line 4? That is because, understand this thing, this is something which is very important. If I consider any 2 points on this line, okay, if I consider any 2 points on this line, let me consider this as my point A and point B. If I map it to the x-axis, if I just map it to the x-axis, I'm just assuming that if this is 1, this is 2, this is 3, this is 4, this is 5. Similarly, over here, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so 10, 9, 8, 7, 6, 5. Okay, somewhere over here is 5, which maps to this, and somewhere over here is 10, which maps to this. If you observe, when I take these points down on the x-axis, how much are these 2 points on the x-axis? On x-axis, I am having just the difference in between these 2 points as 1 unit. That's exactly what we see as this difference. Whereas when I observe this difference on the y-axis, if I project this point, the difference is this much. So on the y-axis, this is as good as 5 units. So I say over here, the slope of line number 1 is this, because on the x-axis, if I move, if I say on x-axis, if I move by 1 unit, then on the corresponding y-axis, there is a movement by total 5 units. If you observe the same thing over here, if you observe this point as C and this point as D, and if you try to find out the movement on the x-axis and you map it to the y-axis over here, you can see that the movement on the x-axis compared to the movement on the y-axis will be not as high as compared to line number 1. If you compare this in line number 3, it will be more or less, and compared to line number 4, it will be more or less. In fact, if you consider a line which is something like this, and if you consider any 2 points, the movement on the x-axis, let's say if this is 3 units, what is the movement on the y-axis? 0. The moment on the x-axis is 3 units and the moment on the y-axis is 0. That happens when the slope of the line is equal to 0. Do you understand this technical implications of understanding slope of the line? What is positive slope and how is one slope greater than other? And what is the significance of understanding this? We understand this by saying that 1 unit on x-axis is equal to how many units on y-axis. That is exactly what is called a slope. Does this make sense to all of you? This concept clear? Because this is very important. This is the main heart of understanding the ridge and the lasso regression. Very good. So this basics is clear to all of you. Now, okay, now that we understand what is the significance of this, now let us understand this equation. So now what did we do over here is, if I have the same thing over here, maybe this is my expense and this is the salary of a person, and let's say these are the only 2 points. Okay, these are the only 2 points, first point and second point. And if I consider this particular thing, this is going to give me the line of best fit, which is overfitting. This is my line of best fit, which is overfitting, because these are my testing data. And to make sure that this model does not overfit, I do this jugaad. Yes, I call it a jugaad only because we are regularizing it. What is regularization? Somehow we are trying to reduce it. Somehow we are trying to reduce the coefficient. Therefore, we call it a jugaad only. It is one of the technique with the help of which we try to reduce the number of coefficients. Okay. Now, let's try to understand it with the help of an example. So I say, let me assume over here that the value of lambda is equal to 1. This is what we have chosen. So now, in our case, what is this particular term? In our case, this particular term is equal to 0 plus. What is the value of lambda? The value of lambda is equal to 1. And what is the slope of this line? The slope of this line is, I have to just assume some value. Let me say the slope of this line is 1.2. So if I say 1.2 square, that turns out to be 0 plus 1.12 are 144. So 1.44, which gives the answer as 1.44 for this particular thing. Okay, so I have my error to be not 0, but error is 1.44. So yes, I get some value of error. Okay, now what I say is, I am going to reduce the slope of this line. Okay, how am I going to reduce the slope of this line? Well, by tilting this line. So let's say I have now, I want to increase the bias as per the point. So let's say I have reduced the slope of this line. You can see over here, if you compare this as line number 1 and this blue as line number 2, obviously the slope of the line has reduced. Let us say that if I'm talking of this blue line, in that particular case, if I want to calculate my error over here, I'll just write it freshly. So if I got to calculate my error in this particular case, I say my error is going to be, this term is 0 plus lambda is still 1, but the slope has reduced. In this case, earlier the slope was is equal to 1.2. In this case, the slope has been reduced, let's say, to 1. So that is going to be 1 square, which is going to be 0 plus 1 square, 1, which is 1. So did you notice over here that the error has now reduced? Okay, you observe over here that initially the error was high. Why was the error high? Because the line had a higher slope. Higher the slope, higher the error. Lower the slope, lower the error. That's exactly what we wanted. I mean, if you remember earlier, the line of best fit was giving us zero error because of this. But now, since I did some kind of jugaad by multiplying lambda with the square of the slope, I see over here that as and when I'm decreasing the slope of this line, that is, I am increasing the bias and decreasing the variance, I see over here that the error term got reduced from 1.44 to 1. Wait a minute. Can you further reduce the error? Yes. To how much power? To how much value? That's a hyperparameter choice. I cannot comment on that. You have to keep on trying it. And therefore, I conclude over here that with the help of Rich, we are able to reduce the value of the coefficients. So now we understand that this taking square of it is going to help me. And now, in fact, let me tell you that if you can even think of a line which is going, something, the line will never go to zero. Okay, zero slope is just not possible. You are not allowed to go. But what happens is if you go to a line which is having a slope almost zero, so let's say the slope of this line is 0.001. Now, if the slope of the line is 0.001, if you multiply, substitute over here 0.001 and you take the square of it, ultimately you will always be left with some kind of error, and that's exactly what you wanted, because zero error, you observed that it was overfitting. So now lasso will ensure that it never comes to zero. It will never come to zero. It will always have some kind of error, and that's exactly what we wanted. Now we wanted to move from no bias to low bias, and this will ensure that. And my lambda is going to be used as a hyperparameter choice over here. This is exactly what happens in case of my last ridge regression. Now, exactly in the next case, okay, let me contradict this exactly in the next case by proceeding to my lasso regression. So if I talk of lasso, what happens in lasso is the same thing. I say my cost function over here, sorry, my loss function over here is going to be I is equal to 1 to n y minus y actual the whole square plus lambda into magnitude of the slope, not the squaring of the slope. Earlier, I used to take the square of the slope. Now I say I'm going to take the magnitude of the slope. And this is going to give me a guarantee that, yes, by taking the magnitude of the slope, when I actually do the multiplication, okay, when I actually do the multiplication over here, I know that the value of the lambda can be 0 to any positive value. In this particular case, since you are doing the same thing over here, expenses versus the salary of the person, since you are trying to address this issue of no bias to low bias, when you take the magnitude of the slope, sometimes, okay, sometimes what happens is if this line is made as good as flat to this, having a value which is very, very near to 0, 0.001, what is going to happen over here? In this case, my error, anyways, this was 0, so this is going to be 0. Even if the lambda value is 1, the magnitude of 0.001 is going to be 0. So 0 plus 1 into 0, which is 0. So because of this, you get the coefficient straight away reduced to 0. Are you able to get it? How is lasso different from ridge? Lasso, by taking the magnitude of it, if the slope is higher, the magnitude can be kept to a higher value, something greater than 1. But if the slope is very less, lasso will directly eliminate that particular thing, and this is how it helps in feature selection. So all of these are nothing but jugaad ways of doing it. Okay, there is nothing, nothing scientific about it. It is just about how to make sure that our model regularizes, and therefore the name also says regularization technique. They are regularizing the things. Okay, nothing as specific as to why using this approach. You can always invent your own regularization technique by whatever mathematical geometrical intuition you want. Absolutely not a problem. Do you all get this thing? Okay, are you all able to get this thing? I'll come to your questions, Srijesh, but let me first take the overall opinion. Very good. So, okay, let me come to Srijesh's question. Srijesh is asking, we increase the bias by changing the slope to 1. We increase the bias by changing the slope towards 1. Doesn't that mean that the first term in the ridge regression is non-zero now? The first term in the ridge regression is non-zero. Which first term are you talking of? Okay. If you are increasing that particular, see, Srijesh, understand this thing. Okay, I understand what you say. With respect to that particular thing, yes, the first term would be non-zero. But what if the data points are this? In this case, this is how the line of best fit is going to be. And now you are going to further reduce it. I hope you are understanding it now. Not necessary that the data points will always be like this. It could be something like this also. It could be something like this also, right? So it purely depends. Okay. So now I think it's the good time to move on to the implementation. How much time we have? Okay, 20 minutes. I think that should be more than sufficient. So I have two case studies for you. One is going to be a very simple case study so that you understand how the ridge and lasso regularization works. And the next is an actual case study, which I am going to give you a walkthrough of. Let me just where is my mouse? Oh. Mm. Okay, done. Just go into the folder for regularization. What is your batch number? DSC 19. DSC 19. Okay. Yeah. Thank you very much. New. The implementation is very simple. You don't have to do a lot. It's as good as implementing linear regression. DSC 19 regularization and lasso. By the way, before I proceed, I will just like to know it from you. Are you all people aware of Grid Search CV? Yes, I'll share the notebooks. Don't worry, Ignority. Very good. So my work has reduced tremendously. Okay, just give me 30 seconds. Okay. Now, is the concept of ridge and lasso 100% clear to you? Other than the implementation part, theoretically, mathematically, geometrically, is the concept 100% clear? Very good. Not 100%. Srijesh, why? need to just work more on bias and variance thing. That I already told you that this concept has to be clear to you, bias and variance. Okay, so let's get started. So this is the very simple case study, and then thereafter you can actually start. I'll show you a walkthrough of the actual case study also. So initially, let me say I'm going to import warnings as usual, and then I say warnings dot simple filter no. I'm going to use a built-in data set, therefore I say from sklearn dot data sets import load underscore Boston. Okay, that's the data set which I'm going to use, built-in data set. Then I say import numpy as np, import pandas as pd, import matplotlib dot pyplot as plt. Let me load the dataset. I'm sure you all know this. Load underscore Boston. Okay, my data frame is being loaded. Let me just look at it. So this is the entire data frame which is being printed. You can see over here, it is in the form of a dictionary of NumPy arrays. You have data, we have target. These are my target values. You have feature names, you have description. So if I say show me maybe df, right? Df dot data. This is my x. If I say df dot target, this is my y. If I say df dot description, this is the description of the columns. You can read it later on, and for it to be printed, I think, let me just try it in print statement. I think it should be printed nicely. Yes. So this is the description of the column. We are not going to go through it. You can go through it. Let me tell you what is this data set about. Okay, as and when I proceed, I will tell you what is this data set about. Well, it is, I mean, in short, I will say that it is the house price prediction data set. Okay. After that, if I want to see only the features, I can always say df.featurenames, and all of these features are available over here. In fact, everything got printed when I just printed df. I mean, if you just observe over here, I'll just show it to you. Df.data printed me this thing. Df.target printed me this thing. Okay, df.featurenames printed me this thing. df.description printed me this thing. And what else do you have? I think yeah, we have df.filename also. We can try that. That is going to print me this thing. Let's try that. So if I say df.filename, that is going to print me where is this particular file. Okay, you need more practice. Yes, certainly you can definitely try that, but at least from my side it's clear, right? So okay, I want to convert this to a data frame. In fact, if I look at the type of df and sklearn's util bunch object, it is a bunch object which is nothing but a dictionary of numpy arrays. That is nothing but called as a bunch object. Let me convert it. So I say let my data set b is equal to pd dot data frame, and we say df dot data. Well, let me tell you over here that when I say df dot data, it is nothing but my capital X, that is my independent variable. So if you want to see it, you can just say print for me data set dot head. Okay, and all of these numbers are automatically labeled as 0, 1, 2, 3. I don't like it, so I say dataset dot columns is equal to If feature names, so feature names is going to automatically do that. And now when I say dataset dot head, all of my columns would be automatically numbered. So let me tell you, all of these are nothing but my independent features. I also want my dependent feature over here. Okay, so for that, let me first of all look at the shape of this. So I say dataset shape is going to be 506 and 13. Okay, and if I say my older one df dot target, what is the shape? 506. So it's matching. So I say over here in my data set, I want you to append a column which is called as price, and that is going to be df dot target. And now when I say dataset dot head, you can see that this price column has been appended over here. And if I look at dataset dot shape, earlier it was 506 rows and 13 columns. Now it has been modified to 506 rows and 14 columns. Okay, so things are perfect as expected. You think till now is nothing new, right? Till now everything is fine. This is something which we know. Now, before even going ahead, what we are going to do, we are going to implement using linear regression, then go to ridge regression, and then go to lasso regression. But before that, I really want to know that, I hope all of you know the concept of cross validation. Yes, cross validation concept is known to everyone. Yes or no? Okay, specifically the k-fold one. Okay, very nice. Perfect. So let's go ahead then. Say over here that I need to work on this. So I say, let me populate my X. My X is going to be dataset dot ilog. I want all the rows, all the columns except the -1th column. That is my X. My Y is going to be dataset dot ilog. I want all the rows of the -1th column. Okay, so if I just say I want to look at X dot head, this is what I have, and this is what my Y is. Okay, so X and Y are perfectly being taken out, and now I think it's the right time that I can go for implementing linear regression. So how to do that? I simply say over here from sklearn dot model selection import cross val code, and I say from sklearn dot linear model import linear regression. Let the name of the object be star is equal to linear regression. I'm not giving any hyperparameters at the moment, and I am going to use my function of cross validation score, which is going to take this our object, which is going to take X, which is going to take Y, and I am also passing the scoring. Okay, I'm not doing any, I'm not doing train test split over here. We'll do it later. Right now, just look at the base one. How does it help it? Okay, although you could have tried train test split before that also. So I say my scoring is going to be, I'm going to give over here the negative mean squared error. Now, negative mean square error. See, mean square error is going to give me a positive value. Negative mean square error is going to give me the negative version of that. Why do we do that? The reason for doing that is the cross validation score is always going to give you a minus error in negative terms. Okay, it is somehow designed in such a way that the error is already given in negative terms. So to overcome that, we write a negative sign over here. That is the reason we write it. Okay, So over here also the error is going to be negative only, but you have to interpret it as positive. And one more thing, this negative error should be as close to zero as possible. And I say, how many folds do I want to try? I say I want to try such 5 folds. And let me store it in messy. Then I say I'm going to calculate the mean of this mean square errors. For that I say numpy is mean of messy, and I'll just print out this. And you, not MSc, I'm sorry, I got to print mean of MSc. I want to print the mean of this. I don't want this. So mean is minus 37.13. So this is the kind of negative mean square error that we are getting it. I will try applying ridge now and see whether this value can further be reduced to as low as 0. That's exactly what is our aim, right? The value should be as small as 0. So now let us go on to the ridge regression. So I say from sklearn.linear model import ridge. Then I say from sklearn.model selection, I am going to use grid search CV because we have to select the correct value of lambda, right? I say import grid search CV, and then I say let the name of the object be RD, which is ridge is equal to ridge. So just like using linear regression, you are going to use ridge. So it is not different, right? And I have parameters. Now in this parameters, I am going to try out different values of alphas. Alpha is nothing but lambda. Okay. Usually in coding, I prefer to write alpha. So it is nothing but lambda, okay, what we just talked of. And I am going to give it various values of alpha to be tried. So let me give it in the form of a list. The first value is 10 raised to minus 15. Second value is 10 raised to minus 10. The third value is 10 raised to minus 8. The fourth value is 10 raised to minus 3. The fifth value is 10 raised to minus 2. Sixth value is 10 raised to, I think, 10 raised to minus 2. Then let us say B8 1, then B8 5, then 10, then 20, then 30, then 35, then 40, then 45, then 50, then 55, then 100. I'm giving just all the possible combinations. Okay. Now let's call grid search CV. So I say ridge regressor is equal to grid search CV. This is going to take the object RD, is going to take the parameters to be tried, which is parameters. I'm going to give the scoring as the same thing. So let me just copy this rather than typing this. So I say over here, that's my scoring and 5 folds. And then I say ridge regressor dot fit x comma y. So yes, you can see over here that the training happened very quickly, and it did try total with 5 folds for the following values of alpha and this. Now let us find out which is the best value of alpha. So I say that by printing ridge regressor dot best score. So best value or best score turns out to be minus 29 point this, and let me look at the best parameter also. So best params, okay, I'll just take this up. So at alpha is equal to 100, I got the value as minus 29 point this. I mean, if you just compare it with what value you got, with linear regression you got it as minus 37, Over here, you got it as minus 29. So yes, definitely a better approach. Are the things clear so far to all of you? Yes. Is this thing clear? Implementation of this 100% clear? It's simple, right? In fact, with this, you can actually do any problem. This is just a generalized code. You just have to fit in your X and Y and you are done. Lata is saying, if I need to understand this alpha or parameter, will it tell the value of lambda? Alpha is nothing but lambda, Lata. Alpha and lambda are one and the same thing. The only difference is in this PPT, when we talked of, we were talking of, or we were calling it as lambda, but in this notebook, we are calling it as alpha. Else, both of them are the same thing, Lata. Okay, don't confuse yourself. Lambda in there, over here, it is alpha. Both are same thing. Usually coding terminology, they use alpha, and therefore I don't want you to deviate from this. So I mean, the reason why I also did it, because if you read a lot of research papers, or if you read blogs on the internet or any articles, everywhere you will see that they write lambda, lambda, lambda whenever it comes to explanation, precisely theoretical explanation. And every time when you go to the implementation part in the notebook, you will see that they always write alpha. So I want you to be acquainted with the same terminologies, but let me tell you that alpha and lambda in our case are one and the same thing. So please don't confuse yourself. It's the one and the same thing. Okay. Yes, very good. Now let's move on to the lasso. Lambda will a way to reduce the existing value of the slope that it got from linear regression. Yes, yes, Lata. Now, going ahead to the next one, lasso regression. Okay, so we are very near to it. So now I say from sklearn dot linear model import lasso. See, there are many versions of lasso. Many versions of lasso. You can understand how deep is the study which you require. This is just mere lasso. Lasso also exists with cross validation. Lasso Lars. I also don't know what is Lasso Lars, Lasso Lars CV. But one thing is sure that if you know Lasso, understanding all of the others are going to be, they will be just somewhat here and there. You just need to go on Google and find out what is Lasso CV, Lasso Lars. But they're going to be very much close to what is Lasso. Then I say from sklearn dot model selection. I'm just writing it once again, okay? There is no absolute significance for that. When I create a lasso object, create an object of this, then I want parameters. I'm not going to waste my time. Control C. In fact, I think I can just make copy all this three. And I paste it over here. My parameters are going to remain the same. This is not Reg regressor. This is my lasso regressor. Object over here is ls. Parameter scoring, everything remains the same. Okay, this is also this, and let me fit it. Now, as usual, initially I'll be finding the best parameters. So I say, oh my god, I did a big mistake. I'm really sorry. Forgot to change it. I'm sure you might have realized it in the chat. Okay. Okay. And then I say lasso regressor dot best params alpha of 1. Okay. Lasso regressor dot best score minus 35. I mean, if I just compare it, I mean, I'll just love to write a cell over here. This is my linear regression, and this is my ridge regression, and this is my lasso regression. What is the value which this gave? Lasso gave me the value which is this. I'll just paste it over here for comparison. What did the ridge regression give me? It gave me this value. I'll just paste it over here. And my linear regression happened to give me, just a second. I'm sorry. Okay, I can call out later. My linear regression happened to give me this value, which I just pasted over here. Now, you are of the opinion that when to go for what. You can see over here that linear regression, ridge regression, and lasso regression. You can clearly see that ridge regression is the clear winner over here. I'm not concluding that ridge is the best, but I say that yes, in this case, we understand that ridge regression seems to be a better candidate. Okay. Now, of course, if you want, you can also do train test split now and do the other things. I'll just go ahead. Does standardization or scaling have any effect to regularization? Of course, it will have an effect on regularization, because regularization is anyways going to reduce on the coefficient. So if you are going to go for regularization technique, you did not go for scaling. Okay, scaling is not recommended when you go for regularization, else you will be scaling the scaled value again. This is what we don't want. So don't do scaling whenever you are going for regularization. Regularization itself is another way of scaling. I hope you are getting this concept, Nitish. Regularization is another way of scaling it. So it's not different. Okay, so don't go for scaling when it comes to regularization. Perfect. So now that we understand this, let us first of all divide the data. Okay, so I say over here, maybe from sklearn dot model selection import train test split, then I say my xtrain test ytrain ytest is equal to train test split. This is my x, this is my y, this is my size. Maybe I divide it into 20, 70, 30 split, and this is my random state. Let's say it be equal to 0. Okay, so train test split is done. Let me ask the lasso to do the prediction. Okay, I should ideally be fitting it, but anyways, I'm just skipping that particular step. You know how to fit it. Once again, call the same thing and do it. But let's say I will directly predict on the X test now. I could have done it. Okay, I could have once again trained it. Maybe if I want, I can just try it with the values. Finally, with the best value, I can do it. But this time, the regressor has to fit on only X train. So if you want, you can actually do this thing. Okay, I can say over here, I want the same thing, and this can actually fit on X train and Y train. Rest everything is going to remain the same. Okay, and after doing this, let us ask it to predict it. But again, in this case, our values are going to change. So if I say over here, we went for ridge, right? So I'll just copy the values for ridge regressor best parameters. Okay, alpha changed over here, and I say ridge regression best score, right? That is minus 22. That has to change, of course. So what I'll do is, okay, let's keep it like that only, or rather, fine, let's try with this. Now I say this is done. Let us do the same thing with the help of lasso as well. So where is my lasso? Here, control A, control C. I ask it, and this time this is again X train and Y train. Rest everything remains the same. That is also there. Then I call lasso best params and best score once again. So lasso best params and lasso best score. Okay. So this is what we have. I'll just copy it down. Just a second. Comparing. I'm not taking linear regression now. I'll just copy it. Let's get rid of this. And what is the value of the lasso which you got is this. So lasso gave me this value, and what is the ridge regression giving me? This value. I say that's the value of ridge. Okay. Huh? Are you sure? Minus 22. Okay, yeah, it has to be minus 22 point this. This is what is the value of ridge. Okay. So very near, right? So in this case, you can see that ridge is still the winner, even if I talk off this. Perfect. Now, let me ask the predictions to be there. So I say red underscore lasso is going to be lasso regressor dot predict, and this prediction has to be done on this test. Then I say let me store the same thing for pred underscore, I mean ridge, and then I say ridge regressor dot predict on test. Since we are doing ridge every time first, what I'll do is just cut this and paste it. Okay, initially ridge and thereafter lasso. Okay, so my predictions are there. Now I'll just plot the distribution to finally see. Okay, rather than looking at the RMSE values, I'll just look at the distribution and literally see whether they are better. So I say import Seaborn as SNS last 4 minutes. Then I say SNS dot plot, and this time I'm going to say over here that whatever are my y test minus my pred ridge. This is the first type of plot which I want. Oh, mistake, this plot. And this is going to be pred lasso. Let us do it and look at the distributions. 1 and 2. Okay, both of the distributions are there. Let me reduce it. If you observe, first of all, in the values of the comparison, okay, if you observe, ridge is having a lower value as compared to lasso. The first one is for ridge and the second one is for lasso. You can see both of these charts over here, and not a big difference over here as such, but definitely if you closely observe it, this is comparatively a more smoother curve than this. Not much, but yes, certainly much more smoother than what we got. Okay, so this is how you can actually do feature selection or feature reduction using ridge and lasso. So I think that's it. After that, if you have any questions, because we happen to do everything over here, every other concept, anything which you think is not covered, which you have any questions, you can certainly think of asking me in the chat section. Where are we passing the value of alpha in the model prediction? Okay, see, whenever you are predicting the model, you need not pass the values. See, you don't what is the basic significance of grid search CV? Grid search CV is going to try with all of the value of alpha, and by default it is going to select the best value. So by default it will select the best value. By default, this thing you need not tell him now. That is the main purpose. Grid search CV will compute with all the available values, and whichever is the best, it will use it for all the further computations. You need not supply it explicitly. Are you getting it, Pawan? Okay. Okay. Any more questions? Till then, I'll just launch the final session poll. That's very important. So request you all to first fill it up, and then you can type in the questions. Whatever questions you have, you can type it and be very specific when it comes to feedback. Properly rate the session. Be very serious because we take it seriously. Your feedback is important, so please ensure that you are very serious when you update it. Okay. 17 of 19 received. Two more. Please fill it up, guys. One more is expected. Done. Thank you very much. Okay, I'll just move to the chat section. Thank you, Darshan. It was, as usual, awesome session. Okay, thank you very much, Nigna Reddy. Any more questions? If you have, you can just ask it, or else we can call it a day. Perfect. So I think it's the good time to conclude. Yes, I'll be sharing the notebook. Don't worry on that part. Thank you very much. Yes, thank you, Pratima. Thank you, Gargi. Session was clear and easy to understand. By the way, how was the session compared to the older live session? Because I didn't take the first part of it, therefore I don't know. I mean, if you compare it with the older session, was it good? I mean, did you get any additional information over here, or it was the same repetition? Yes. Thank you, Nitish, Ajinkya, Prajakti. Oh, it was completely different. Matthew, thank you. Completely different. I mean, was it weird in my case? Because the matter has to be the same. Contents has to be the same. I mean, how the things can be different? No, content was a bit different. Okay, content was a bit different, but as far as the understanding goes, is it clear 100%? No, the way of explaining the things are more easy to understand. Thank you very much. In fact, this is the feedback which I get from all of my learners. No, everyone says that I make it easy. I don't know how, but I just teach the usual way I am. That's the good thing in your session. Thank you very much, Gargi. Content is same, but the way you explain is super. Thank you, Nigna Reddy. That was more theoretical. Okay, yeah. That, and this was both. Okay, that was two. That two was good. Okay, she finished the session with the introduction to Lasso and Rich. Okay, fine. Okay, understanding was good here. As per understanding, it is very clear. Very good. So ultimately, the moral of the story is now it is 100% clear. Perfect. As per my understanding, it is very clear. I would say both the sessions are complement to each other. Very nice. Okay. Fine then. Let's call it a day. Thank you very much, participants. See you all sometime later in some other session. Bye bye. Have a good day. Happy weekend. Thank you, Anaga, Srijesh, Ajinkya. Thank you, Nigna Reddy, Pavan, Sandeep, Srijesh. Thank you very much, Lata, Gargi. Happy weekend to you too. Thank you, Pratima. You too take care.